Go. Okay. We were supposed to do integration competition today. However, I'm not going to be here for period 6. So, period 6, kiddos, this is for you. We're going to save integration competition for tomorrow. And what we're doing instead today is we're going to be grading if it's up. Ooh, it's not up, but it's coming up. We're going to be grading our evens from the homework that's due today. So have your homework spirals out and your colored pens at the ready, because we're going to see how all that antiderivative stuff went. I can get your textbook open as well on the webcam. But before we grade homework, I want you guys to open up notes, because then you're going to throw your pencil in your notes, close it, we're going to go grade. Open up notes. I want you guys to start section 4.1b. Ooh. So the section we covered, integration, antiderivatives, the basics, was A. Yep. We're going to cover 4.1b, or at least start covering it today. But here's how 4.1b starts off. AKA, there's another book homework. The other book homework is the second half of the homework. If you guys noticed, maybe you didn't really notice, but we did a lot of the, like, hey, it's just a, well, actually I can show you on the webcam. Homework was a lot of, hey, it's an integral, solve, it's an integral, solve, it's an integral, solve. Now, they asked it a few different ways. It wasn't always an integral, sign, and solving. But did you notice that there was, more to homework? Does anybody notice that? What do you notice on the pages that we didn't really do yet? Words. Oh. So 4.1a was basics of antiderivatives and indefinite integration, just like the title says. But then it was like, well, now that you know this, let's apply it to word problems. Now, don't worry, not all word problems, but rate, movement, motion problems. Rate is most obviously seen for most of us in motion, and then it gets applied to weird things like the water filling a tank, or the snow falling on the ground, or the bananas being taken off of the display at the grocery store, all those weird FRQ things the AP might bring up. But before we get into those crazy word problems, we're just going to be talking about motion. But what do you guys notice I'm having you start the motion section off with? Review. Isn't there a motion forever card? And weren't you supposed to study your forevers for the quiz that we took when we came back last week? I want you, from off top of your head, to write down as many motion facts as you know, specifically from calculus, but maybe you have, like, I don't know, the gravity constant memorized? Anyway, whatever you remember from the motion forever card, and or if you have any sort of physics background knowledge, that might be helpful also. But write down as much as you remember. And then if you're like, okay, that's it, that's all I got. Okay, open up your forevers or go back to where we covered motion the first time. Go to your table of contents. Where did we cover motion the first time? It was very similar to this. We covered basic rules and then we applied them to motion all in one section. I think it was an A and a B. Go see if you can find it once you get stuck. Motion is position and velocity and acceleration. Too many hints. Period 6, kiddos. At this point, I need, as soon as someone has finished, Gavin, you're closest to the front table. Yes, I'm talking to you. This is weird. I'm talking to Gavin in the future, but I am in his past. Anyway, timey-wimey. On the front table, Gavin, there is a stack of motion packets, and it is in like the middle between the coffee pot and the hanging files. Anyway, go on up and go ahead and pass it around the room to everybody. Make sure everyone gets a motion packet. We're using it a little bit today. Period 1 kids, you already have it. But if you look on your Google Calendar, or if you look on Google Classroom's kind of hard because you're not going to necessarily see the motion packet because it's like a separate handout. You're not doing pictures of the motion packet at any point. But if you look on the back board, the bookwork, the one in Google Classroom, is due Thursday, so not tomorrow, but the next day. The motion packet is due on Friday, and we're going to be working in class on the motion packet mostly tomorrow and Thursday. Sound good? So it's kind of classwork, but it's going to be finishing for homework, and not the entire thing, but bits and pieces. So tonight your main objective is to get into the book problems. Tomorrow is to finish the book problems and get into the packet. And then Thursday night is to finish the packet. Anyway, just to give you a kind of precursor of what's coming. All right. So period 6 kids, you're writing down formulas. Gavin, when you're ready, you're passing out those motion packets to everyone. Get your name on them. And then we'll be ready to go as far as motion. Did you guys figure out where motion was the first time? No one mentioned it?
Forever number 11. No.
Okay, forever number 11, but where was it in our notes? Because we started motion with derivatives, and now we're finishing it with integrals. Where did we do motion the first time?
2.2b?
Yeah, that sounds about right. 2.2a was, what was 2.2a? Basic derivative rules?
Yeah.
Awesome. Kind of like we did basic integration. So 2.2a is like our 4.1a, but the derivative version, and 2.2b is like 4.1b, the motion portion of it. Does that kind of make sense? So if you get stuck on motion, could you maybe go back and look at 2.2b to remember at least the basics?
Yes.
But our forever card is supposed to remember or remind us of that also. So what are some things you guys wrote down? Doesn't have to be in the forever card order, but it could be. What's something underneath motion that you already know?
Average rate of change.
Yeah, good. So average rate. And then Andrea, you're saying it. So S of B.
Minus S of A
All
over
over
B
B.
minus A.
And specifically, this isn't, remember rate is just how fast, but how fast of what? So it could be average rate of position would be technically the snazzy way of saying this, or another way of saying it would be average velocity, right? Because velocity is the rate of change of position. So average velocity is S of B minus S of A all over B minus A. What else do we know? Okay, so we could have, even before we got to rates, we could have talked about position itself, and position itself is S of T, or X of T, right? S or X is usually what they say. Could be Y of T if we're talking about parametric motion. But what else? We did position, we did average velocity.
Instantaneous.
Instantaneous velocity. Now we don't usually put the word instantaneous, even though it's true. We just say velocity, because if we're talking about velocity, we're talking about instantaneous, not average. Average needs to be stated for us. How do we find instantaneous velocity, which is V of t? Who's that?
S prime of t.
Yeah, take a derivative, right?
DSDT.
Now, in the video that we watched with the organic chemistry tutor, he said that the instantaneous can be approximated by the average, or the tangent slope can be approximated by the secant slope, right? The average and instantaneous relationship. And on his video, please, 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 it's not always like this. On his video, the average equaled the instantaneous. That's very, 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 very special. That's only an MVT kind of thing. He just happened to have it equal. Usually it's just going to be close. That was one of the things I was kind of disappointed with his example, but that's okay. What else do we know? Position, average velocity, velocity, instantaneous. Ah, speed. Yeah, he's still in here with rate of change of position, but he's the one where the sign does not matter. It's also known as, I'm not sure if we wrote it in our forever card, I don't think we did, but it's the magnitude of velocity. It's the how much, regardless of whether velocity has a positive or a negative sign, aka if the motion is increasing, going to the right or up, or decreasing, going to the left or down. Ooh, increasing or decreasing. We have forever cards to help us with those words that we didn't have back in section 2.2. What else?
Acceleration.
Acceleration, nice. Whose acceleration? The rate of change of?
U of t.
Yeah, he's the rate of change of velocity as indicated by the prime, by the derivative, right?
S double prime.
Or, good, or he could be the rate of change of the rate of change of position. Remember, we can always take that little prime, that little derivative, and change it for the word rate. Change it for the word rate. And anything that could possibly change can change at a rate. Not just motion, not just distance, but also how much money is in your account, or how much, or the temperature of biscuits who have just been pulled out of the oven, or let's see, temperature. We already talked about snow. We already talked about water. Number of people in an amusement park. That can have a rate. Anyway, just reminding us that word problems are coming, and who knows what's going to be in those word problems. Did you guys come up with anything else?
Just free falling salt.
Okay, we have some clues. Yeah, good. We have some clues. We have some clues like acceleration for like a free fall model. Did we talk about this? Yeah, it was in your directions. I'm not sure this is in your forever card, but for a free fall model, we can say that acceleration is a constant, and acceleration is equal to negative gravity, which would be either negative 9.8 if it's in meters per second squared, or it could be negative 32 if it's in feet per second squared. That's something that was in your directions back in section 2.2, and you were just able to like put it into a formula. But you also had things like, Adam, you said hit the ground. What's going on if I hit the ground? The position is 0. I might not know the time, because it could be on the ground to begin with, or it could be hitting the ground sometime later. I don't know the time, but I do know the position. If it's something about at rest, what would that mean? Or be saying if
Like
something
initial?
is at rest?
Like initial?
Oh, there's initial too. We can keep thinking about at rest. I might not have put that in the forever card.
No.
Some things come up later rather than earlier. Initial, that means time is 0, right?
Yes.
At the beginning. Or it could be like initial, could be at 9 a.m. and maybe they're measuring hours from midnight. So maybe T is 9. So just thinking about the beginning of the time, which is usually 0, but it could be something else. At rest means velocity is 0, because it's not moving. Does that kind of make sense? At rest, velocity is 0, which also would mean that speed is 0. Anyway, do we know stuff about motion?
Mm-hmm.
Yes. But in all of these, do you see any integrals?
Nope.
Of course not. We were just learning derivatives. Do you remember that? We had just learned the power rule. Bring down the n, make it n minus 1. We had just learned basic derivatives. So all we saw was moving forwards, aka going from a quantity, and then its rate, take a derivative, and then its rate's rate, take another derivative. But that's how derivatives work. Derivatives say, and we're going to keep it with the green because it's review, derivatives say, hey, we're thinking slope, hey, oh, that's another slope. There's another one. We're thinking slope, we're thinking rates, we're going forwards, but I'm going to get a blue because it's new. What are integrals going to do?
Go reverse it.
Be able to go from acceleration to velocity, and from velocity to position. Integration is going to go backwards. Wait a minute. In the word problems that the organic chemistry tutor did, wasn't there one where you had the amount function and you were trying to figure out how fast? And so we took a derivative. But wasn't the second word problem the rate function, and we were trying to figure out the amount? You haven't seen a lot of AP FRQs because they can go forwards or backwards, and until you learn integration, can you go backwards? Mm-hmm. So, anyway, we have some fun stuff coming. But before we start applying integrals to motion and moving on, let's go ahead and make sure that you guys at least have the general idea of antiderivatives. Is that good? We're not going to spend like forever. Oh, I'm trying to make it so you can see all of this. Forever and ever. I'm going to try and make it so you guys don't, or we don't today, spend tons of time on homework. I want to cover the basics and make sure you have the basics, but then I'm going to wait until I'm with both classes tomorrow. Integration competition, we'll start class off with that. We'll see if you guys are getting better and better and better at doing antiderivatives. So we'll just cover the basics of homework. Sound good? You guys can go ahead and write this down and get ready. But we're not going to solve this example yet. We're going to put our pencil, close our notebooks as soon as you have it, and then colored pens, homework spirals. Let's check those antiderivatives. If we need to be going backwards in motion, we have to at least be able to go backwards first. Because then we start having words and it just makes it more complicated. Or maybe for a few of you, it makes it more practical. Like, oh, there's a point to this.
This is all my pointless.
So many math words. So many English words have math meanings. What else but a math class would you have to be careful about the difference between complex and complicated?
English.
Or distinguish and differentiate. Or, I don't know if I have another one. Those are the ones that I have to be really careful of all the time. So I say something about complex and I'm like, oh, imaginary. No. Complicated. Or let's differentiate, let's derive, and I'm like, no, we're not taking a derivative, but fine. or distinguish. Struggle. Optimal. Ooh. Optimize.
Optimization.
Although that kind of goes together because they're synonymous. Just in calculus, you have to actually think about, derivatives and relative extrema and absolute extrema. Oh, you guys on your forever quiz. Absolute extrema. You have to test the critical numbers and the endpoints, right? My ones that gave me just how to do the relative extrema. It's okay, period 6. I asked relative and they gave me absolute. I think some of them talked to you. Awkward. They missed it. A partial credit. You would be seeing them, except I think we have one person. Jane, have you taken your forever quiz? Come talk to me. Just not today. I'm not here. But I think we have one or two that haven't taken it yet. So. Yeah. Remember, I'm talking to the future.
Hi,
Hey, Izzy. Aw, they're all saying hi. Okay, come back.
Hey, Izzy.
All right, you guys got it? Did you get the example problem? The ball being thrown up with an initial velocity from an initial height, and they want us to find the position function. Hey, it's like the organic chemistry tutor's problem. They wanted a function or something to do with the amount, but they knew the how fast. Same thing here. We have a velocity, we have a rate, we have a how fast, and they need to know the position. Okay, pause. All right, enough. Let's go grade. We've gotten into motion sufficiently to at least have something to build off of. I'm going to come over to our forevers. Ooh, I totally need to update these poor little forevers. We've been sitting up here. We guys had quizzes and forever finals and whatnot. I need to update.
Joe.
But as you guys start grading, I'm going to scroll down a little bit and I'm going to get the motion card up on the wall, period 6. Look over. I did it because you'll be able to see it.
Crazy.
Right? The present, the past, the future, all coming together in one video.
Adios, Cory Booker.
P.S. You're supposed to be grading these. Wait a minute, checking? Why are they checking? Because any integral can be checked by taking its derivative. Any integral can be checked. Kyle, you said forever number 11, right? There it is. Any integral can be checked by taking its derivative. Not my favorite, but I think almost everyone says that. Except for Kathleen. You better not say that because you're just. Okay. Did someone just compliment Kyle on his name?
No.
Oh, I thought you said thank you, and I was like,
That was George.
Because I did a high point.
I was like, that'd be good.
Here we go.
So weird. Sometimes you do and don't. Can I move down?
Yes, fine.
No, guys, is this original, sorry for my period 6, guys, is this correct? Could you have stopped here? Yes, but what are they doing here?
Check it.
No, that's down here. What are they doing? They're just making it match, right? They're just making it match. Remember, just like with derivatives, you have to be careful.
Making it match. I got the negative.
Drew a red kind of cross.
Okay, let me scroll down.
Nice, kids.
Stay in school.
That's really happens
Bloop,
every time.
bloop. Number 18, you can see, once again, making it match. So negative exponents, in general, they're putting in their proper place. Remember, it's kind of hard to see sometimes, but like number 18, there is a negative in front. There's a little baby space. Maybe some of you see it, maybe some of you don't. But there is a negative in front because a positive over a negative is a negative of the whole expression. Number 26, you had to know your, did you multiply first? We don't have a product rule for integration. We had to have distributed first and then matched it up with integration rules from the trig. Do you have your signs right? Do you have your trig right? Did you see the dy and the functions in terms of y, and so you just kept the y in there, hopefully. Number 28, it was a power rule with a trig rule. The sign had to flip. Can I keep going?
Yeah.
So far, so good? Oh, 44! Why was he a mess, but not really?
There's so much to do.
How many integrals did you have to do,
Too many.
to get all the way back.
It's like
Too many? Get it? Too many. You had to do two integrals because you had to go backwards one step from the second derivative, and then you had to go backwards again from the first derivative. A second derivative had two derivatives taken. I need two integrals to completely undo. Hey, could this be like an acceleration? And this be like a velocity? And then this be like a position? But you guys had to use all of your clues because you had to figure out the first guy's plus c, aka like the velocity or the first derivative's plus c, and then you also had to figure out the second guy's plus c. And if you guys notice, see how they use the little subscripts to try to distinguish between the two? I mean, I guess you could do like C and D and, well, E's a number, so that's awkward, but C and one other subject, be careful of using the letter E. Or the Greek letter pi. Just kidding. Hopefully everyone knows pi. Anyway, final answer, -2 ln of, ooh. You ready? This is not a good make it match form. It's not a good one. You ready? Here's the best one for like an AP. Yeah? Ln of 1 over x squared with no absolute value plus 6x minus 3. Why are they the exact same thing?
You actually switch the ln to.
You switched to absolute value.
The absolute value is gone. What did I do? Remember, according to logarithmic pre-cal properties, can't the -2 come up?
Pre-cal property.
Pre-cal. Well, we reviewed it.
Oh, yeah.
We reviewed it in the summer packet. But the -2 can come up. Wait a minute, but where'd the absolute value go? Well, one step at a time. What does -2 mean? Doesn't it mean 1 over x squared, guys? Where'd the absolute value go?
It went away.
Why did it go away? Yeah, Kathleen, why does the absolute value no longer have any meaning if there's an x squared?
because if you plug in any number into the x squared, it's going to be positive.
Exactly. An x squared is always going to be positive. What does an absolute value do? Keep it positive. It's redundant. It's unnecessary. It's irrelevant, so it's gone. Does that make sense? Okay. I respectfully disagree. Okay, so anyway, the books is great and all, but for the AP, keep going to make it match. LNs, they love making those constants into powers. And they love taking away the absolute value when possible. Anyway, that one's pretty nifty. You had to take 2 antiderivatives, and oh my goodness, the evens are done. Now, does that mean the hard problems are done? No, I think I heard that the last two, like 49 and 69, were kind of gross. Anybody agree with that?
69 was okay.
Oh, 69 was okay. 49 was not okay?
It was 49.
Oh, I gave you one with words. Did I really? Isn't that just mean of me? But wait, doesn't this sound kind of like the organic chemistry tutor's problem? Except instead of, that was the guy's name, he does calculus.
That's the one we were watching.
Okay, you guys were very into the cards at that time.
Oh my gosh.
Give me that.
Name him Jared.
Jared?
Jared.
You want to call him Jared?
Can we call him Jared?
Well, that's his handle, so I just.
How about Jared? Jared is his new name.
Jared the OChem dude?
Jared the OChem dude. There we go. Jared. I like that.
Poor guy. Don't know if his name is Jared or not.
Why not?
Okay, so Jared the OChem dude. David and him are tight. Anyway, so remember how the amount of water and the rate of water, or we were given the rate and the amount? Check it. This is a tree. It's a shrub. It's a nursery. I don't even know. But is there a rate? Yes. We don't care about the shrub and the tree and that. We probably should somewhat, at least a little bit. If you like gardening, go team. But they give us a rate equation. And what are they asking for in letter A? Height. Do you see how the shrub really doesn't matter? Yes. Rate, amount, integrate. What's going on? I don't know. But rate, amount, integrate. Now careful, we can't just for the AP completely ignore absolutely everything to do with the words that they're giving us. But in general, for right now, I am totally okay. If you see a rate and you see an amount and you say, I need to integrate. Where's the plus C, Adam? Did they forget it too? No, because there was a clue.
Oh, wow.
And whenever there's a point, whenever there's a clue, whenever there's an amount at a time that I can plug in, you should be able to find the plus C. So we would have plugged in that T was 0 when H was 12, and then C equaled 12, which is why it's plugged in. Anyway, remember, we're not supposed to spend forever on homework today. I can go over further questions tomorrow right before integration competition. But do you see why I showed you that video before we started this semester?
No.
Now, when we're it's okay, hang in there. When we keep going, today we're going to go into motion. Motion has to deal with gravity and like velocities and accelerations. And so this is just the beginning. But to be honest, this is more helpful for the entire AP and FRQ section, number 49 is, than all the stuff we're going to do today. Because for the AP, they're not just going to have like position, velocity, acceleration. They're going to have, Anna, something is changing at something, and then we have to think about what it was to begin with. And we have to kind of not see the words velocity or acceleration or position and still be able to know what to do. So today is super important. Motion is super important, but I'm just reminding you of the big picture. All kinds of different stuff in this world can change. Ooh, everything changes? That's kind of hard, but true. However, we're going to take just a second. We're going to take today and tomorrow and Thursday to focus in on one specific type of changing, which is motion. Now, really quickly, in the evens that we covered before, I shouldn't even say before, 49, 69, we might see if you guys have questions on those tomorrow, or if you need me to show any more work on those last ones, because I think PK was working on. PK, did you figure out 69? If not, ask me tomorrow. But anyway, was there anything before the word problem started showing up? 44 or earlier that you guys just need me to talk through real fast? Kathleen? 44. Okay, let's peek at that one real fast, and let's go back to motion. 44 is not on this page, is it? No, it's not. Okay. 44 is over here.
This is off topic, but what's the schedule for today?
Normal?
I don't know. It's not today.
What is it?
Yeah.
Yeah, is there?
There is a surprise something at 9 o'clock that we forgot the football field for, but besides that.
She says the abortion assembly was not today.
No, not today.
I thought that was next
For that, it's like a special chapel. I think it's next week, and they're doing things like permission slips and Bible classes, and if your parents don't sign it, you're not going to be in there anyway, and stuff like that.
Oh.
But your Bible teachers should be talking to you about it today.
There's a surprise.
I'm not starting it.
Fire drill. Oh.
What period?
9 o'clock's the next period.
Yes, Abby.
Okay, don't spam me the entire campus with the fire drill. Can't let everyone know. Okay, anyway, sorry, I thought that's what you guys meant. I was like, how did you know? Anyway. Kathleen, it's this one, right?
Yeah.
Okay, did you realize, I'm going to go straight to the answer key. Did you realize second derivative, you have to go backwards 2 steps? Did that make sense?
Because I got 41, so I knew how to do 44, but I think I made a mistake along the way.
What did you get for f prime of x?
I got negative 2 over x in the square.
Oh wait, that's good. Okay, so hold on. That's solid. And then you went to go take that one's integral. Did you get to ln after that?
No.
That's why. You saw that negative, I'm guessing, because you should have gotten the plus 6x, I think, right? And then plus c. Did you get that part? Okay. What you messed up on was the 2 over x. But you probably thought of doing a power rule. And in thinking of doing a power rule, the problem is you would have had to have added 1 to the top and to the bottom. Ooh, Miss G is listening to this. My grammar has to be perfect. So negative 2x to the negative 1 plus 1. I have issues. Exactly. But no. This is a perfect thing. Because if you look in your notes on the integration chart of the basic rules that we've learned so far, why does it say that x to the n dx integrated is x to the n plus 1 all over n plus 1 4? Why is there more to it? Do you guys know what comes next?
Plus.
Oh.
And because I negative 1.
The one time the power rule doesn't work, and technically it's stated in the rule that you're putting on your forever card, but your brain is going to remember this and forget this. is because -1 doesn't work, which is actually a huge blessing, because it's like a ding, 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 ding. Oh, that's right. What's the integral of x to the -1? He's going to look like he should be made into a power and used for power rule, but he's illegal. And he starts making stuff look real nasty, dividing by 0, DNE. No. Remember, it was an ln. Does that make sense? So it's actually a huge blessing that it messed you up, but you just need to then go ahead and be like, oh, that's right, 1 over x. Well, okay, the -2, remember, he can just be a constant, so I could think about the 1 over x on his own. Sorry, I'm just keeping the rest of it because it was, the integral of 6 was a little bit easier. So I'm just zeroing in on the integral of 1 over x. But yeah, that was just supposed to point you to, hey, it should have been an ln. And then I just talked about how that -2 can become a power, and then we can simplify. But yeah. Good catch though, kid. It's going to happen. Okay, notes, motion, and grab out your motion packet, guys. Notes, motion, and grab out your motion packet. We might do a little bit, or we might technically not do anything in the motion packet today and do most of it tomorrow. Grab out your motion packet, have it at the ready, just in case we can sneak it in. But what's most important for you guys is to do examples like the books that you guys can tackle that textbook work. Okay, remember, period 6 is listening to all of your extra conversations. Okay. Yes, Anna.
When you integrate 1 over x, I should be writing the actual value. I don't have that in the notes. Does it just always actual value?
Yes, it was on the integral formula. Yeah. The rest of you guys put ln of absolute value of x in your integral formula, right? You're in your notes. Peek back real fast. Did you write down the integral of 1 over x is ln of absolute value? Just double checking. Okay. Good. Problem solving steps. Hey guys.
Yes.
How unfamiliar do these 3 steps look?
Not very.
Because isn't it how you basically tackle any and every word problem ever?
Yeah.
Right? What are you given? Can you draw a picture? What are you supposed to find?
Related rate.
Do it. It's a lot like related rates, but it's a lot like optimization. It's a lot like motion to begin. It's a lot like any word problem ever. Right? We got to read it. We got to understand what they're giving us, and then what we're supposed to find, and then use all of our training and our skills and our notes and our examples, all of our resources to figure out how. So I have solved ... because in related rates we kind of solve one way, in optimization we kind of solve another way, in motion we kind of solve another way, but it's just using basically everything you've ever learned in math and in calculus. Yay! And maybe a few things you haven't. So, you guys have already written that down. Can we go tackle an example problem?
Sure.
All right. If you said no, it'd be too bad anyway. So, here we go.
Joe.
What are we
Doing today.
Don't have to worry about that yet, John. Let's just talk about what are we given. Then we'll figure out what we're supposed to find. Then we'll worry about what we're actually doing. So, ready?
Yes.
Give me a fact about this problem.
Initial velocity is 64 feet per second.
Can I say initial is v of 0 or shortcut it to v sub 0 and then I can say 64 feet per second? That's snazzy?
Yep.
Cool. Why is it a positive? Because velocity, remember the sign matters. Speed, it's irrelevant because we're just talking about magnitude. But velocity, the sign matters. Why did I make it a positive and not a negative?
The things are on upward.
Thrown up. So the motion is in the upwards direction. If it was in the downwards, what would I have made it?
Negative.
Negative. What else do I know?
Initial height.
Good. So I could say S of 0 or S sub 0 is 80. Could I draw a picture?
Yeah.
I guess. I mean, how else are you going to have an initial height of 80 if you're not on top of something? True? Is it a building? Sure. Is it a pyramid? Why not? Is it a plane? Be very low, but sure. Are you bungee jumping? And it's, I don't know. I'm giving up now. A ride at Magic Mountain? Possibly. But anyway, don't throw things off roller coasters. 80 is how high? Is that good? And from 80, my ball is being, now remember, it's super awkward. You're leaning over the ledge and you're throwing it straight up, and then it's soon going to go straight down. Remember the whole awkward one-dimensional motion? Straight up, straight down, no arc. That has to use BC stuff. But anyway, straight up, then straight down. Got him. Letter A, what are we supposed to find?
Position.
Function.
Position, function. So aren't I supposed to find S of t? Right?
Yep.
And then letter B says find when does the ball hit the ground?
0 for velocity.
So A is just the function S of t, and B is when what 0?
Velocity. Or t.
No. That's just what you're finding. You're finding time. You're finding when, right?
What time
Yeah,
when
when.
the positions?
How long it takes or what your time is when the, why is Adam saying position when Kyle a second ago thought velocity? Most common mistake in these types of problems, but that's correct. Why does it have to be position and not velocity? Because things go splat. You hit with a velocity. After you're on the ground, is your velocity 0? Hopefully there's not something like pushing you through the cement. But you hit the ground at an impact. But where are you if you're on the ground?
0.
Where are you? You're at 0. I know where you are, I just don't know how fast you're hitting. What's the only time you would hit with a velocity of 0? The only time I can think of is if you're bungee jumping and you barely graze the ground, meaning you have a negative velocity and you're about to have a positive velocity. What's the difference, or IVT, what's going to happen between a negative velocity and a positive velocity? A 0, and if that happens to happen perfectly when you hit the ground, if that's that vertex, if that's that minimum, that's the only time you'll have a velocity of 0 when you hit, which is really you're just grazing, barely touching the ground. Is that going to happen? Probably not. Okay, so we got to do it now, right? All right, John, now it's time.
Figure out.
What are we doing? Yeah. What are we doing?
Integrate.
Finding.
We do need to integrate, but the problem is I would love to integrate the velocity function, but do I have a velocity function or just one known velocity?
One number.
So ready? This problem has background information that without which you wouldn't be able to solve. Ready? The background information is that this is a free fall model. Meaning there is absolutely no acceleration except for gravity. This is one of those back in section 2.2 you would have had to have read the paragraph above the problem to be like, oh. Because if you have a free fall model, if it's just like something's being thrown, something's being dropped, something's being this, that, or the others, and there's no accelerator pedal, there's nothing actually adjusting its velocities during the motion, it's just being let go and going for it, it's called a free fall model. And here's something we can know for free fall model. First of all, there is constant acceleration, which means the acceleration function is just a constant. A of t is just going to be negative gravity. So I don't know v of t, but I do know a of t. I don't know the first derivative, but I do know the second. And what do we do in number, Kathleen, you said it was 41 and 44? What do we do if we have a second derivative and we have to go all the way back to an original?
Do it twice.
2 integrals. But hold on, if this is always going to happen in free fall models, maybe we can do it over here off to the side and you guys just use it. Physics kids would be like, let's memorize it. Calculus kids would be like, let's just understand it and be able to come up with it ourselves. Constant acceleration. How do we get velocity from acceleration? We integrate. We say we need to go backwards. So velocity says, let's go backwards from acceleration. So in this case, we can say, oh, sweet. Well, since acceleration is just gravity, ooh, hold on. Is it feet or is it meters?
Feet.
Good. So we're going to come backwards of negative 32 feet per second squared. Now, I put the units in just for us to see them. We can kind of think of it as dimensional analysis, including the units in the math that we're doing. But really, it's just the integral of negative 32. And that's just a defined what gravity is in feet per second. So maybe that's something helpful for you guys to write, or maybe it's going to be in those paragraphs above your problems, but gravity is either, or I should say acceleration, which is negative gravity, will be either negative 32 or negative 9.8. I think we wrote that in the page before, but just in case. Sorry, squish. Writing it now. So how do I take the integral of a constant, guys? Put a x, but
Or
wait,
t.
d who?
T.
Put a t. And don't forget your plus c. Wait a minute, but those of you guys that were finding plus c's last night, if they gave you a clue when t was 0, what did c always end up being? If t is 0, isn't c just going to be the other guy? So the nice thing is for motion, I'm able to say that c, ooh, that's awkward, most stanza, that c is going to be my initial velocity. Just because plugging in 0 will make that negative 32t go away, and my initial velocity will equal to c, I'm able to make that extra jump. So technically, physics people, if they ever memorized a free fall model of acceleration, velocity, and position, would have memorized your initial velocity, gravity times t plus your initial velocity, which could be v of 0 or v sub 0, different ways of writing it. If we're doing physics, it'd be more like a subscript. And so it'd be a of t plus b sub 0, or a sub naught of t plus b of 0. We could, but we also have to do position. Do you guys think that we can take another integral?
Yes.
Gravity is gravity is gravity, as long as you're on the Earth, for the most part. If you're in different places on the Earth, it changes very slight amounts. But we just use these nice little rounded numbers. So we can actually go back to position also. And we can say position is integrating who?
Yeah.
Velocity. Good. Do you guys see maybe some new forever card formulas coming? Position says, let's go backwards from velocity, so we can actually take this velocity guy and say, hey, it's going to be gravity, or I should say acceleration, times t plus whatever my initial velocity is. That's going to be what I integrate. Well, guys, hold on. How would you integrate a constant times a variable? Wouldn't that be 1/2 times my negative 32 and then t squared? Wouldn't you add the power and then divide by? And then, wouldn't this just be a constant, so it'd be v sub naught t? And then wouldn't I have a plus c? But the crazy thing is that plus c is going to be my initial position.
There's a lot of
If you guys go back to section 2.2 and go to those paragraphs that you needed to use for your formulas, you would have seen something like, for a free fall model, position is always known as 1/2 acceleration t squared plus initial velocity. Plus, you saw it in pre-calc and you saw it in section 2.2, but now you know how to get it yourself. It just starts with gravity and says, oh, hey, take a couple integrals. Dun, 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 dun.
Oh my gosh.
So what does that mean? Well, actually, this is quite an easy problem. Because can't we just plug in? And can't we just plug in? And can't we just, come back and remind ourselves that 80 was how tall the building was, not how fast. It should have been feet and not feet per second. Oh, sorry, x is another way of saying position, remember?
Oh, yeah.
All right, CalcAB, goodbye with you. Don't worry about your motion packet. We'll come back to it tomorrow, but you have it ready to go. But tonight, play with motion in the textbook. Don't worry about the packet at all. Period 6, I'm not here after school. Period 1, I'm not here after school. I'll see you guys tomorrow. 0 period, I'll be here. The coffee should be on the timer in the future. I think so. I think so. Because technically it's 4.1. The math isn't any different. You're just learning, motion, I can go backwards. Bye, guys. Wish me luck in algebra.